In this video we'll study additional ways of factoring polynomials and introduce you to 3 important theorems about polynomials. In factoring polynomials, so far we have only investigated polynomials that had a leading coefficient of 1. But this isn't always the case. Here is an example of a polynomial with a leading coefficient of 2. Suppose you need to solve this equation. In factoring it, ordinarily we look for the factors of 4 that also add up to 9. But the coefficient of the squared term prevents us from doing that. What we can do is divide both sides of the equation by the coefficient of the squared term. In this form we can use the familiar factoring technique, with a difference. Since the constant term is a ratio, we need to find the factors of the numerator and denominator. These are the factors of 4 and 2. So the possible factors of the polynomial are the ratios. Let's test x equals -4 using synthetic division. We get these two linear factors. To remove the fraction, multiply both sides of the equation by 2, and we get these two linear factors. This method of factoring polynomials is summarized in the rational root theorem. For a polynomial with integer coefficients, the roots of the polynomial are of the form p over q, where p is a factor of a sub 0 and q is a factor of a sub n. Let's use the theorem on this cubic. First identify the factors of the constant term, -9. Then identify the factors of the leading coefficient. Then identify the possible roots of the polynomial. The synthetic division shows a test for x equals 1, which turns out to be one of the roots. The factored form is shown at the bottom. The graph of this function shows that the cubic intersects the x-axis just once. This means the quadratic term has complex roots, which you can find using the quadratic formula. The rational root theorem is very useful for finding potential roots of a polynomial. But what happens when a given rational number isn't a root of a polynomial? This gives rise to another polynomial theorem. Let's start by looking at this cubic. First find the factors of 8, then the factors of 4. Then find the possible roots. The synthetic division shows that x equals -1 is a root of the cubic, resulting in the following product of a linear and quadratic. The graph confirms that there is just the one real root at x equals -1. But what if we tested x equals +1 as a root? Using synthetic division once again, we get this result. The 20 that you see here is a remainder. But doesn't remainder imply division? Yes. Here is the full division statement showing the remainder of 20. And there is one other thing to notice. This remainder is also the y-coordinate for the function, at x equals 1. This gives rise to the remainder theorem. When a polynomial p of x is divided by a linear factor x minus a, the remainder is p of a. This is summarized by the equation shown. Let's look at the equation in more detail. Dividing p of x by x minus a can be accomplished through synthetic division to find the polynomial q of x and the remainder. This is very similar to what we just did with the cubic polynomial. How is the remainder theorem useful? Here is a problem you might encounter in working with polynomials. Evaluating a polynomial simply means substituting a number for x and calculating the result. However, this polynomial would have you doing a lot of calculation. Here's how the remainder theorem can help. Rather than grinding through higher degree polynomial calculations, use synthetic division with x equals 8, as shown here. While the synthetic division has its share of large calculations, you'll find it to be a much easier way to evaluate the polynomial. While the remainder theorem is useful for evaluating polynomials for specific values of x, it's just as useful for finding linear factors of a polynomial. Let's take a look at the equation from the remainder theorem. The polynomial q of x was the result of dividing p of x by x minus a. The remainder was the value of p of a, but if x minus a is a factor of the polynomial, then there would be no remainder, which means that p of a equals 0. This gives rise to the factor theorem. When a polynomial p of x is divided by a linear factor x minus a, with no remainder, then x minus a is a factor of p of x. Is binomial x minus a the factor of this polynomial? Let's use the factor theorem to determine this. We can also use the rational root theorem to identify candidate roots. Look at possible values for p, q, and the ratio. As you can see, x minus 1 is a potential root for this polynomial. Let's use synthetic division to check. As you can see, x minus 1 is a factor of the polynomial because it has a remainder of 0. The three polynomial theorems we've reviewed are the rational root theorem, the remainder theorem, and the factor theorem. Here's an effective way of using these in combination. 1. Use the rational root theorem to find possible roots of a polynomial. 2. Use the remainder theorem to evaluate the polynomial for specific values of the function. 3. Use the factor theorem to find one or more linear factors of a polynomial. These theorems, along with the ability to graph a polynomial function, give you a lot of tools for working with polynomials. There is one more theorem to review, the fundamental theorem of algebra, which you can learn about in the next and final video in this series.